So, we proved that the set of non-zero fractional ideals in a Dedekind domain forms a group under multiplication. We use that to prove that any non-zero ideal in a Dedekind domain is a product of prime ideals, and the way to write this as a product of prime ideals is unique up to ordering. So, as a corollary of that, today we are going to prove that any fractional ideal is a ratio of prime ideals, product of prime ideals, which means that you can write it as a product of prime ideals, but exponents are allowed to be negative integers as well, right. And then we will prove a version of Chinese remainder theorem for Dedekind domains. Okay. So, here is a corollary of last time's theorem. Let R be a Dedekind domain. Okay. Any non-zero fractional ideal A of R can be written as A is P1, sorry, this is product up to Pm over Q1 up to Qn, where Pi's and Qj's are prime ideals. Okay. And none of the Qj's is equal to Pi's and vice versa. So, this is not in, this is not in, I mean one of them is enough, but let me write it this way. Okay. And this way of writing is unique. This expression is unique up to ordering again. Right. And of course, the hard part was to do it for integral ideals, and now we just do it for fractional ideals. Okay. All right. So, let A be a fractional ideal as in the statement of the corollary. Okay. So, there exist x in R minus 0 such that x times A is an integral ideal, is a non-zero integral ideal. So, which means that x times A, this is P1 up to Pm for some prime ideals Pi. So, P1 up to Pm. Now, what I do is I consider the ideal x. Okay. So, x is Q1 up to Qn for some prime ideals Q1 up to Qn. Hence, A is P1 up to Pm excuse me times Q1 inverse up to Qn inverse. Right. This is another way of writing P1 up to Pm, Q1 up to Qn. Now, that is not quite done, because we may have we did not choose our x carefully enough. So, there may be some common primes in numerator and denominator. So, we cancel out, right, because we know how to multiply by inverses of prime ideals. We cancel out common primes from numerator and denominator. Right, and so that gives factorization. We still need to prove uniqueness. Okay, so if A is P1 up to Pm, Q1 up to Qn, which is also same as P1 prime up to PL prime, Q1 prime up to Qk prime, then we get Q1 prime and so on up to Qk prime, P1 up to Pm is equal to P1 prime up to PL prime, Q1 up to Qn. Now, the point is that, so now we have equality of two prime factorizations of ideals, and we already proved uniqueness there. Okay. So, each of this Qi must appear on the each of this Qi prime must also appear on the right hand side, but it can't appear in Pi primes, right. So, hence so it must appear in Qi. So, hence M is equal to L, N is equal to K, and Pi is equal to Pi prime, and Qj is equal to Qj prime up to reordering. Okay, so it's an easy consequence of the previous thing that we proved. Okay, all right. Now, let me remind you what the classical Chinese remainder theorem over Z says. So, remind Chinese remainder theorem which I will write in short as CRT over Z. So, let me just tell you the simplest version of it. If M and N are integers, or let us say natural numbers. So, okay, M and they are both bigger than equal to 1, and GCD of M and N is equal to 1, then Z modulo MNZ is isomorphic to Z mod MZ cross Z mod NZ. And what is the map? Well, the map in this direction is given by, you take A mod Mn and you send it to A mod M comma A mod N. Okay. So, there are two things to prove about this map. First, that it is injective, and second, that it is surjective. How do we show that it is injective? Well, if an integer is divisible by M and it is divisible by N, then it is also divisible by the largest common multiple of M and N, and the largest common multiple of M and N in this case is Mn, because GCD of Mn is 1. Right. So, that is why this map is injective. And then we want to prove that this map is also surjective. This is exactly saying that you want to solve a simultaneous congruence. So, it is also stated in terms of a congruence, right. But again, the point is that M is invertible in Z mod NZ and N is invertible in Z mod MZ, and so you choose their inverses, and that is what you work with, right. So, let M be in Z mod NZ such that, or let me just write it in the usual manner. So, be in Z such that m m is congruent to 1 mod n. So, we can always do that and let n be in Z such that n n is congruent to 1 mod m, right. And so, if A, okay, let me use a different letter, if B and C is in Z mod m Z cross Z mod n Z, then you can take A to be right. So, what should you take? You should take right, B times So, modulo n, sorry, modulo m, you want B, right. So, B n n plus C m m, right. So, what is this? So, this is congruent to B modulo m, and it is also congruent to C modulo n, right, because mod m, this second term vanishes and the first term is just B times 1, right. Okay. So, we are going to use the same idea. What do we want to do? So, here is theorem, Chinese remainder theorem. So, let R be a Dedekind domain, okay. Let A, which is P1 to the N1 up to Pm to the Nm, be a non-zero, be a non-zero ideal of R, okay, and Pi is not equal to Pj if I is not equal to j, right, and Ni is greater than or equal to 1. Then R modulo A is isomorphic to product I going from 1 to m of R modulo Pi to the Ni. Okay. So, this is exactly this reduces exactly to Chinese remainder theorem over Z when R is equal to Z. Okay. All right. So, how do we prove this? Again, we need to prove that the map is injective and that the map is surjective. Okay. So, what I do for simplicity is I define, so I will define this map again, but now instead of going mod A directly, I will write it like this. And what is the map? Well, R goes to R modulo Pi to the Ni. Okay. So, now injectivity, first we prove injectivity, which means that the map is 1 to 1, and because this is a ring homomorphism, to show that it is 1 to 1, you just need to show that any element that goes to 0 is actually 0. Oh sorry, not injectivity, I mean, so we want to show kernel is A, right. So, it is not quite injectivity, it is injectivity from R mod A, but let me write it that way anyway. So, let R in R be such that R mod Pi to the Ni is equal to 0 for all i's between 1 and m. This means that R is in Pi to the Ni for all I between 1 and m, right. But again, because these Pi's are distinct, this means that R belongs to product which is equal to A, right. And so, hence R mod A injects into product I going from 1 to m R modulo Pi to the Ni. Okay. So, this hooked arrow means injects, injectivity, all right. So, now I want to prove surjectivity. Okay. All right. So, we use the same idea that we used over Z. So, we take R 1, let me write A's, R's are a bit hard to write on this board. So, I take A 1 up to A m in product I going from 1 to m R mod Pi to the Ni. Okay. So, these AIs are in R mod Pi to the Ni, but I will just think of AI as an element in R up to some multiplication by up to some adding an element of Pi to the Ni. Okay. All right. So, what do we do? What I do is the following. So, right. So, I consider Pi, okay, not Pi, maybe rather than doing it generally, let me do it for P1. So, this thing, and I consider P2 to the N2 up to Pm to the Nm. So, since Pi's are all distinct, these two are none, I mean the first ideal is not contained in the second and the second ideal is not contained in the first one. So, what I do is I let A1 be in P2 to the N2 and so on up to Pm to the Nm minus P1 to the, or let me just write it as minus P1. Okay. So, there will always be such a thing. Okay. So, similarly let AI be in P1 to the N1 up to Pi minus 1 to the Ni minus 1, Pi plus 1 to the Ni plus 1 up to Pm minus Pi. Okay. So, you take everything out of this product except the ith term and let Ai be in this, but not in Pi. So, there exists Bi in R. So, I should say the following first. Oops. Okay. So, as Pi is a maximal ideal, R mod Pi is a field. Okay. So, there exists for each I there exists Bi in R such that AI Bi is congruent to 1 modulo Pi. Okay, I am deliberately writing the this simply means that AI Bi minus 1 is in Pi. Right. Okay. So, what I do now is I let A be A1, A1 B1 and so on up to AM, AM BM. Okay. And if it is not clear already, then the exercise is to show that A is congruent to AI modulo Pi to the Ni for all 1 less than or equal to I less than or equal to M. Okay. So, this proves surjectivity. And hence the Chinese remainder theorem. Okay. All right. So, here is a curious corollary, I mean it is just a nice way of writing Chinese remainder or applying Chinese remainder theorem. So, let me give you this corollary of Chinese remainder theorem, I will just sketch a proof of this. Okay. So, let A and B be two non-zero ideals in a Dedekind domain R. Okay. Then there exists alpha in A such that, so alpha is non-zero, such that alpha by A is co-prime to B. Okay, and of course, the notion of co-prime now here means that you write alpha by A as a product of prime ideals. So, you write the ideal generated by alpha as a product of prime ideals, and because alpha is contained in A, this alpha by A is an integral ideal, and I can always find an alpha such that alpha by A is co-prime to B, does not matter what B is. Okay, so, notice that in this corollary we are not assuming that A is not B. So, A could be equal to B and still you can find an element in A such that alpha by A is co-prime to A, right. So, it is kind of nice thing, it is a very nice application of this. Okay. So, let B be P1 to the N1 up to Pm to the Nm. So, here Pi are prime ideals, Pi is not equal to Pj for I not equal to j, right, and so this is a prime factorization. Okay. Now, each of this Pi, it may or may not divide A, right. I am not assuming anything about A and B, right. For example, I just said that A could be equal to B, it does not matter. Okay. So, let Li be the largest power of Pi dividing A. Okay. So, what does this mean? This means that Pi to the Li divides A, but Pi to the Li plus 1 does not divide A. Okay. So, Li could be greater than or equal to 0, Li could be 0. I am not saying that Pi has to divide A necessarily. Okay. All right. So, what I do is I take alpha I which is in Pi to the Li, but not in Pi to the Li plus 1. I can always do that because Pi to the Li is not equal to Pi to the Li plus 1. If they were equal, then Pi would be equal to R, because we can multiply by Pi to the minus Li on both sides. Okay. So, by Chinese remainder theorem, there exists alpha in R such that it satisfies the following congruences. So, alpha is congruent to alpha I modulo Pi to the Li plus 1 for all 1 less than or equal to I less than or equal to m, and alpha is congruent to 0 modulo A divided by P1 to the L1 up to Pm to the Lm. So, this is an integral ideal and all these ideals are co-prime, pairwise co-prime. Okay. So, by Chinese remainder theorem we can always solve this congruence. This means that alpha is inside A, and if we look at the prime factorization, this is co-prime to each Pi and hence to B. Right. So, that is what we have done. Okay. All right. So, an amazing corollary of this is the following. So, in a Dedekind domain, so we proved, for example, we proved that a principal ideal domain is a Dedekind domain, but the converse of course need not be true, right. As an example, you take z square root of minus 5. So, we will soon prove that z square root of minus 5 is a Dedekind domain, and we saw as an example that there are ideals in z square root of minus 5 which are not principal ideals. Okay. So, we know that Dedekind domains are Noetherian rings. So, every ideal is finitely generated, but every ideal need not be principal. Well, here is a nice corollary which says that they are better than finitely generated. So, any ideal in a Dedekind domain is generated by at most 2 generators. Any ideal in a Dedekind domain is generated by at most 2 elements. Okay. So, proof, of course, we do not need to prove anything about 0 ideal, because 0 ideal is generated by 0. So, let A be a non-zero ideal in a Dedekind domain R. Actually, it is better than generated by at most 2 elements. The proof will show that you can take any non-zero element in A, then there will be another element in A such that the first element and the second element together generate A. Okay. So, let alpha be any element of A which is not 0, okay, and consider the ideal alpha, this is B. Okay. So, there exist, maybe let me call this alpha prime. Okay. So, there exists alpha in A such that alpha by A is co-prime to B, which is alpha prime. This is the previous corollary, right. And so, now I consider alpha prime, this is contained in A, right. But on the other hand, because these 2 ideals are co-prime, right, on the other hand alpha by A plus alpha prime, this is equal to R, right. So, another way of writing this is that alpha plus alpha prime A is equal to A, which of course means that A is contained in the ideal generated by alpha and alpha prime. So, hence A is equal to alpha prime, right. So, what we proved is that A is generated by 2 elements, at most 2 elements. What we went further, we said that if you take any alpha prime, a non-zero element of A, there exists another element alpha such that alpha prime is equal to A. Okay. So, this is a good point to stop. We proved further properties of Dedekind domain, including the Chinese remainder theorem. Our next task would be to prove that the ring of integers in algebraic number fields are Dedekind domains. Okay. And then we get factorization of non-zero ideals in rings of integers into product of prime ideals.